All right, we can get started right now. So, hello everyone. My name is Harris Wang, and welcome to this presentation. I'm a rising senior at Emory University studying computer science and data science. I'm currently a data fellow at New York City's Department of City Planning. So, in this presentation, I want to share a proof of concept large language model pipeline to essentially geocode projects from New York City's capital planning database. So essentially, like geocoding is transforming from freeform text to coordinates that could be mapped via via like GIS tools and actually be displayed in a visual manner. So let's get started with the agenda. We're going to be providing an overview of the Department of City Planning, the data engineering team, as well as the data source that we'll be working with. And then next, we'll be diving into the project scope and the requirements and such. And then after that, we'll be discussing the actual implementation of the pipeline before discussing more about the project results and future road mapping. So to provide an overview, it's really important to explore kind of the purpose of the DCP, the engineering team, and the data source. So a brief introduction of DCP is that it is NYC's primary land use agency and is responsible for kind of planning construction, growth, and the developments within the city and has a long history of creating essential citywide data products. And we're building kind of new and refactoring existing data sets that we call data products using a variety of open source technologies. And then here are some of like the pillars of the purpose for the data engineering team. So we want to provide high quality products while being highly transparent and automated pipelines, providing full support with documentation and metadata, and supporting a community during the process. And let's examine the data product here. So the data set we'll be working with is the capital projects database, which lists the current and planned capital projects from the capital commitment plan. And here's kind of a snippet of this data set here. And we can see there's a lot of information such as project ID, the agency name, the project type, as well as the description for this project. And we want to provide a more visual view of this by mapping it in a explorer. But as of now, there's no geometric column, which signifies the lat and long of these projects. So what happens is that as new projects are added and the old ones gets retired, these existing geocoding efforts, such as this manual labeling, which is both time intensive as well as incurring like requiring domain knowledge, as well as more simplified regex um, like rule-based NLP methods falls behind. So roughly about 8,000 projects lack geometric data in this latest data set. So kind of to specify the scope of this problem, we aim to convert a project description to a lat and long format that can be mapped via GIS tool. And the technology that we choose is LLM for its ability to analyze like more complex text. And here's kind of like a brief overview of what is an LLM. It's essentially like AI that's trained on massive sets of text data to generate human-like text. So now we gotten more acquainted with the background. Let's dive into kind of the actual implementation of it. So here are the few project requirements outlined here. We want the in pipeline, since there's a lot of data available, we want it to be lightweight, meaning that we want the processing speed to be fast, as well as requiring lower computational resources per project. And we also want it to be free and open source, accurate in the context of our of this task, and we also want it to be secure. So to meet these requirements, we selected an open source model Llama as the base model, and API provide as Cerebrus AI as the AI provider and access via API call, as well as LangChain as a framework to kind of orchestrate this model chain to break down the task into like different model calls. So here's kind of a general overview of the pipeline here. So this black box is kind of representative of the nature of LLM, which is more kind of indeterministic and difficult for us to predict the outcome. So we aim to minimize this uncertainty in this initial step of only limiting the transforming the description into an address with the LLM, but using DCP's internal tool called GeoSupport to actually convert the address, the specific street address, to geographic coordinates. So here's a more high level like demonstration of what we'll be using the LLM for. And here we're going to be like here are like different approaches that I've implemented in this proof of concept pipeline. The first approach, this is a very high level one, is essentially a brainstormer versus a address matcher LLM chain, with the first one listing the clues about the location within the project description, and the address matcher kind of matching a specific either a significant historical landmark or an actual street address from those clues. And this approach, we ran it on a label data set of about 300 records, and we got about like 40% correct matches. But however, out of all the geocoded records that are attempted, about like 60% of them are incorrectly geocoded, which we call the false positives. And why they're bad is that it may cause misinformation with this data being disseminating to the general public, potentially harming government reputation. So as such, we want to find ways to reduce the false positives by providing essentially like more context to the model. Um, so a technique that we use is called few shot prompting, which is used to improve the performance by providing small numbers of examples within the prompt itself. So there have been considerable improvements in terms of increasing the volume of the geocoder projects, but it still falls flat in terms of reducing the false positives. So as such, we turn to a more kind of conservative approach with this second iteration. So essentially, we task the first model call, the address extractor, with essentially just extracting the apparent address from the project description, and the verifier leveraging its external as well as internal knowledge base to verify the validity of that extracted address. So with this approach, we're getting kind of polar opposite results here. Despite only getting about like close to 5% correct matches, we're only getting less than 5% incorrectly labeled ones. So we can discern there's a polarity of performance as well as this dichotomy of the different approaches of high volume versus high accuracy. So kind of after discussing the pipeline, this POC pipeline, as well as the framework, we want to touch bases on kind of the findings as well as the problems that we discovered from this process. So the noteworthy results, we've established a large language model framework in a data engineering setting. So we're making the code modular. We're taking steps to make LLM calls as well as like the different chaining process more efficient, as well as implementing a comprehensive validation framework to assess the accuracy of our results. And then in addition to that, we assess the different LLM approaches, and then understanding that the crux of this problem is to decouple the true positives from the false positives here. So essentially the challenges that we have with the low volume and the low accuracy is this lack of context. For instance, like the domain knowledge, as many agencies have very particular naming references rather than the actual locations, which makes it difficult for the LLM to discern which ones it can actually correctly geocode. And for the hallucination, it it kind of lies within the inherent property of LLM models. So it hallucinates frequently when prompted to perform like greater tasks, such as like associated agencies or like pinpointing agency's headquarters. Um, so potential future directions to add more context to this pipeline. One is that a native to the LangChain ecosystem is called LangGraph, which is an agentic workflow that enables the LLMs to interact with each other with each other in a more sophisticated manner, as well as the ability to leverage like tools or like external web or like external resources. And another is essentially like web access, which allows like provides more contextual cues to assist with the predictions of this pipeline. And special thanks to the Department of City Planning, and thank you all for joining me. Uh, yeah, we can move to the questions. Sorry. Mhm. Yeah, yeah, you can write in the chat as well, or I've I have a few slides kind of prepared that includes like kind of the specific prompts as well as so like if anyone wants to like look over, feel free to say so in the chat. Mm. Yeah, no worries. Yeah, so here's kind of the oh yeah. Yeah, go ahead, Yada.
So thank
Mhm.
you, Iris. Very helpful, and congratulations. So, which part of this project was your favorite part?
I think um good that's a good question. I think overall this project has been very helpful as well as changed a lot of my perspective in terms of like how government views the latest technologies um as being like more accepting than as this like more stereotypical way of like it being very bureaucratic and slow. So I think my favorite part is this freedom to explore the different options as well as seeing as testing these different iterations and get like a better sense of how this technology works. Yeah, I think that would be my favorite part, as we'll likely see that a lot in the future as well. So just be prepared for that. Yeah. Um, was there a okay, let me read the question. Was there a common type of hallucination or most hallucination? Yeah, that's a good question. So I think this so our original prompt is more like a, like a all-inclusive one where there will be like very vague description, sometimes just like with an agency, like kitchen renovation. So we want to test, like to what we want to benchmark kind of the internal knowledge base of the base model. So because of that, a lot of these efforts of the LLM trying to like actually associate these agencies with an actual address has a lot of problems. So only the ones where there's like a very kind of clear street address was it able to match. So I think that may have something to do with LLMs, or at least like the base or the pre-trained LLMs property of breadth over depth. So more work has to be done either with more training or like providing like more context to the base model to like improve its predictions. Yeah. Does that answer your question? Yeah. Yeah, I can also showcase here kind of a more structured prompts that we're having. Um, oh, is there anyone? There's yeah. And yeah, here's kind of like, like the capture all that's having a lot of like hallucination along with like more project descriptions that's being able to kind of extract information from. So and here's kind of a few examples of few shot prompting. So for instance, like the first address contains like a street number and name. So we find that to be a true positive. But in terms of like the second entry where there's a high likelihood of a false positives, because we we're assuming that the model may require extra context in terms of deciphering like NYPD as well as um, yeah. But all right, thanks for coming.